This week we're going to go over 3.6 and 3.8, which will really just be cleaning up and putting together everything we've done up to this point in all of section 3. So to start off with, let's get into 3.6. 3.6 is all about this idea of what are called asymptotes. Now, I want you all to consider for a second this function f of x is equal to 3 over x minus 2. The graph of this function is going to look a little bit like this. My mistake, I just drew that backwards. So the graph of this function looks a little bit like this. You notice there's this line, x equal to 2, that our function approaches but never actually touches, right? And this makes sense because we can't put in the value 2 into our function. We can get as close as we want to it, but we can't put 2 in. This line is called a vertical asymptote. And all an asymptote is a line that a function or an equation may approach, but it can't touch. It can't cross it physically. Like you can go and have 2 different parts of your function on either side of it, but you can't actually cross it, right? So to test for vertical asymptotes, we use the limits as x approaches some value c from the left to the right. So in this case, we have for example, x approaching 2 from the right. Well, when this happens, our function is going to approach infinity. And when x approaches 2 from the left, our function is going to approach negative infinity. We can see that just looking at the graph, right? Like we're going to be approaching this line, but as we do, our function is going to get closer and closer to infinity, right? So as 2 approaches, or as x approaches 2 from the right, our function approaches infinity. And as x approaches 2 from the left, our function approaches negative infinity. This is how we're going to identify where we have vertical asymptotes. Because all we're saying here is that we're not getting close to a particular number. We're getting close to infinity, whatever that means, but not to a particular number here. Make sense what I mean? So this is how we identify when we're going to have a vertical asymptote. If there's a number c such that our function approaches an infinity from the left or the right, then there's a vertical asymptote. So just to reiterate what I've drawn up here, same idea, right? Approaching from the right, approaching from the left. So the definition of a vertical asymptote is as follows. I'm not going to quote it to y'all because I find that to be particularly obnoxious as a student, right? Your instructor reads the slides straight to you. For those of y'all at home, the slide that I am looking at is slide 5. It's the definition of a vertical asymptote. But jumping to the slide after that, we have a bunch of different examples of what we're talking about. So check out this first example A, where we have the function is equal to 1 over x minus 1. Notice there's a c value, in this case 1, such that when our function approaches it from the left or from the right, the limit of our function is infinity or negative infinity. Also notice it's not always the case that you're going to have an infinity and a negative infinity. You can have that we approach infinity from both sides, or negative infinity from both sides. It may also be the case that we don't have just one vertical asymptote. We may have two. So consider the case of x plus 2 divided by x squared minus 2x. We know that our denominator can't be 0. This is where our asymptotes are going to occur, whenever our denominator is equal to 0. So to find out where our asymptotes are, one trick we can look for is with rational functions, setting our denominator equal to 0 and solving for those x values. When we do that in this equation, we find that x is either equal to 0 or to 2. Yep. Having said that, let's consider this case. I'm going to write this on the board. We've got f of x is equal to x squared plus 2x minus 8 divided by x squared minus 4. Well, because we're good mathematicians, let's go ahead and factor these out, both the numerator and the denominator. In the denominator, when we factor it out, we're going to get x plus 4 times x minus 2. That's in the numerator. And in the denominator, we're going to get x plus 2, x minus 2. Now notice we've got a cancellation in here. We can cancel out these x minus 2 factors. When we do, we're going to get that our function f of x is equal to x plus 4 divided by x plus 2. But hey, in this case, x can't be negative 2 or 2, right? In this case, we're saying that x could possibly be negative, or be positive 2, right? So we have to identify that to say, well, yeah, we've simplified it, but the simplification isn't equal to this. Because in this case, there was a value we couldn't be, that we can now be over here. So we have to identify that and say that x cannot be equal to 2 here. And we've simplified our function now. Now notice in this graph, what we've got, if we're going to graph this whole thing, so let me actually flip to the next slide because I'll have a better picture of it than what I can draw. Notice in this graph, what we've got is a vertical asymptote and a point that we can't reach. This point that we can't reach is what we had to take out. And this vertical asymptote is what's left over. Make sense? Because all we've done when we simplified it is we plugged this hole. So now we can apply the limit and find that we have a vertical asymptote whenever x is equal to -2. Vertical asymptote whenever x is equal to -2u. So really this is kind of just a review of what we've done with limits, but now we're putting a geometric interpretation on all of this. Having said that, there's another type of limit that we didn't talk about. It's a limit at infinity. We write this as the limit as x approaches infinity from the left, the limit as x approaches -infinity from the right. Now notice I wrote from the left and from the right here. That's because there's nothing greater than infinity, right? So we can't approach this from the right. We can only approach it from the left. There's nothing smaller than -infinity. So we can't approach it from the left, we can only approach it from the right. Having said that, because we can't approach infinity from the right and we can't approach -infinity from the left, we can go ahead and ignore that and just write it this way. Make sense what I mean? Now let's take a moment to apply this to something we're familiar with. Let's just evaluate the limit as x approaches infinity and -infinity on f of x of 1 over x. Well, as x approaches infinity of our function 1 over x, right? This thing's going to go to 0, isn't it? Because we can keep picking larger and larger and larger and larger values than every other value we've picked previously. And as we do, the only number we approach is going to be 0, right? So this thing must be equal to 0. Similarly, if we were going to have the limit as x approaches -infinity, 1 over x, this thing's going to approach 0 as well, isn't it? Because as we pick smaller and smaller and smaller values, 1 divided by -1, 1 divided by -2, -1,000, -1,000,000, trillion, we're just going to get smaller and smaller and smaller negative decimals, right? And eventually, they're going to approach 0. That's what we're going to see. Agreed? So this thing is also equal to 0. Now thinking about it graphically, you can kind of see this. Notice, as we move further and further left, we get closer and closer to 0, right? As we move further and further right, we get closer and closer to 0. Well, isn't that just another asymptote, but this time it's horizontal? So we also have horizontal asymptotes. And we determine them by evaluating what the limit is at infinity or -infinity. So, if a function is equal to L1 as the limit approaches infinity, infinity, then we say we have a horizontal asymptote at L1. Similarly, as x approaches negative infinity, if our limit is L2, then we would say that we have another horizontal asymptote at L2. As two quick examples of this, we've got this function here, this function here. Notice we can have a limit in both directions. They can be different in both directions. They can be the same in both directions, or we can have just one in one direction. So in the case of a horizontal asymptote, we may cross it at some point, but as we tend to infinity, it's the value that we're going to approach. So notice we cross it here, but as we approach infinity, we don't cross it again. Moving in the opposite direction, we can do the same thing, right? Make sense what I mean? Kind of, sort of. So as another quick example, the limit as x approaches infinity of x minus 2 over x squared. Well, notice the limit of a constant is still going to be that constant. So all we really need to deal with is this limit here, right? Of negative 2 over x squared. But the limit as x approaches infinity of 1 over x squared is 0. So this thing's going to go to 0. We're just going to be left with the 5. So the limit here is 5. If we think about it, this makes sense because all we're doing is shifting up or down, right? We're reflecting this across the y-axis because of the negative, and then we're shifting it up 5 units. That's all we've done here. So if the original function was going to approach 0, this makes sense now to approach 5. You know what I mean? For those of y'all who aren't familiar with the way graphs transform with relation to different addition and multiplication operations, you can check out a review under the Algebra Review tab on Blackboard. And I would highly suggest y'all do that. Having said that, horizontal asymptotes come in 3 sort of flavors when it's about rational functions. This is really what we're going to be talking about in this class more than anything else. So a rational function is the division of 2 polynomials. What I'm saying is, we say f of x is a rational function if, to use the same notation, they've got p up top, q down low. If p of x and q of x are both polynomials, then we would say f of x is a rational function. And we have 3 cases that we might be concerned about with the horizontal asymptotes here. We have the case where the numerator has the highest degree. We have the case where the denominator has the highest degree. And we have the case where they both have the same degree. And the rules apply as follows. For those of y'all at home, this is slide 15. But to really quickly reiterate this, the degree of p of x is greater than the degree of q of x would be this case here at the bottom. The degree of the numerator is greater than the degree of the denominator. In that case, we have no horizontal asymptotes. Low key, I kind of love saying asymptotes because it's the only time I get to say as legitly in a math course. I am that mature. All right, so the second case we might have is when they're equal. In which case we have a horizontal asymptote at A over B, where A over B is going to be the leading coefficients of your functions. So A is the leading coefficient of P, B is the leading coefficient of Q. That sucks because I just dropped that. And then finally, we have the third case. Where the degree of your numerator is less than the degree of your denominator. In which case you have horizontal asymptote at y equal to 0. So as a couple examples of this, we've got 3 different cases. The first case we've got up here is the example where the numerator has a lower degree than the denominator. So based on these rules, we know that the horizontal asymptote should be at 0. Here they're equal, so the horizontal asymptote should be at -2/3. And here, the numerator has the highest degree, so we should have no asymptote. Asymptote at 0, right? Because we're going to approach 0 both directions. Asymptote at -2/3, right? And then no asymptote. No horizontal asymptote in him. So having said that, let's consider this example here. We've got this small business that has an initial investment of $5,000 into a new product. And to produce the product, for every unit it produces, it has to spend 50 cents. So what we want to do is find the average cost per unit of this thing, right? So let's put all of this together. The starting cost function is equal to the initial investment plus 50 cents for every unit we make, right? So the cost function should look like this. Now, we want to find the average cost function. The average cost function is going to be equal to our cost function divided by x. So we're going to get 5,000 divided by x plus 50 cents. Now they ask us to find out what the average cost is at a few different points. They want us to say, all right, x is equal to 1,000, 10,000, 100,000, what is C of x? Average, the average C of x. I'm going to say we're going to skip this and go to that in a second. Before we do, let's notice something about our function. Let's notice that the limit as x approaches infinity, so as we produce more and more and more and more and more objects, more and more units, the inverse of x is going to be equal to, well, that's going to be the limit as x approaches infinity of 5,000 over x plus 0.5 which we can break up a little bit more. Right, we can evaluate this term by term now. Agreed? Well, this thing's going to stay 0.5. This thing's going to go to 0. So what we're going to have is 0 plus 0.5. Having said that, what then do we know about our average cost function? These values should get closer and closer and closer to 50 cents, right? That would make sense, wouldn't it? So evaluating this at 1,000, we're going to get 5 plus 50 cents. So this is going to be 550. At 10,000, this is going to be 50 cents plus 50 cents, a buck, right? At 100,000, this is going to come out to be 5 cents plus 50 cents. It's going to be 55 cents. And we see that it's getting closer and closer to 50 cents now. Comparing our math, 550, a buck 50, or 55 cents. So for those of y'all the other week who were trying to let me know that the mic was off, and having a conversation amongst yourselves during that time, To answer one of your questions, you were talking about not seeing when all of this would be applied, right? Like you're not going to go out in reality and be like, oh, let me just find the derivative of this thing. It's not going to happen. But in a business setting, you might want to know something about the general trend of cost as an average, right? Or something of that nature. Well, this is one application you might have generally just shooting from the hip, right? Of saying, I want to know what my average cost will be as I produce more and more things. Well, instead of actually calculating that outright, you can look at it and say, this thing should get closer to 50 cents, right? So it's a quick hip shot evaluation that you could do there in a business setting. Having said that, checking out the graph of the function, as we approach infinity, we do in fact have a horizontal asymptote at 50 cents. And for now, I am going to skip to section 3.7. So section 3.7 is going to take everything we've learned from all of these different sections and combine them all at once. What we're going to be doing here is building up graphs just using calculus and some basic algebra without having to go through and calculate every point, right? So as an example of what I'm talking about, we might imagine a function like f of x is equal to 1 over x plus x cubed plus x to the 4th plus 1 over x to the 5th. I have no clue what this graph looks like. And in order for me to graph it, without using the techniques we're about to talk about, we'd have to go through and calculate a bunch of points, right? We're going to have to calculate a shit ton of points, just because this function is not going to be a nice, smooth function. It's going to have all sorts of bumps throughout it. For those of y'all at home, I challenge you to graph. Actually, you know what? I'll graph it right now. All right, so I had 1 over x plus x to the 3rd plus x to the 4th plus 1 over x to the 5th So this is kind of hard to see, but what you've got here is kind of a snaking graph and a U here, right? And this is just zoomed in to the x-axis being from negative 17.5 to 17.5 and the y being from negative 10 to 10. So what does this graph look like? For those of y'all at home who can't see this very well, it looks something like this. Now, to graph this, you're going to need a whole bunch of different point values, right? Because you're not going to be able to catch that snaky sort of structure right away. You're not going to be able to catch that U sort of structure right away without using a whole bunch of points. So that's going to suck. You're going to need a bunch, 10, 20, 30 maybe. However, there's a shortcut, a trick to this where you don't have to evaluate a whole bunch of points. And that is what this section is all about. So this section is all about using calculus and some basic algebra to figure out what your graphs are going to look like. This is what I've kind of been hinting at over and over again as we go through lectures, where I'm like, notice we can kind of get some of our graph back now. So let's consider this function right here. X cubed plus 3x squared minus 9x plus 5. People at home, anybody got an idea of what that's going to look like without graphing it? Any thoughts?
No clue.
No clue, right? Like it's not obvious right away just looking at that. But we could go ahead and say, let's factor out our function. We're going to find our intercepts. In particular, we're going to find our x-intercepts. So I'm going to do this on the board as we walk through the solution to this problem. All right, so our x-intercepts are going to be at 1 and negative 5. Negative 5. We got another one at 1. Actually write these as points. Now, we know if we take the first derivative, factor it, and set it equal to 0, we're going to get critical numbers. In particular, we're going to get a critical number at 1 and at negative 3. So let's go ahead and add negative 3 to our graph now. That's going to be somewhere around here. Well, this tells us something automatically about our function as it passes this value 1, 0, right? We have a critical number at x equal to 1, and we know we pass through the point 1, 0. So the critical number is going to tell us that this thing is either a min or a max right here, right? It flattens out somehow. Make sense what I mean? So, now moving on to the second derivative and factoring that out, we find we have an inflection point whenever x is equal to negative 1. So let's add that to our graph. Now, applying our derivative test to the first derivative and to the second derivative, we get that we're concave down with a relative max at 3 and negative 3. We're concave down from negative infinity to negative 1. Right? Actually, let's go about this slightly different way. Let's start by looking at the first derivative test. So we're increasing on the interval negative infinity to negative 3. That's this interval, right? We're decreasing on the interval negative 3 to negative 1. We're decreasing from negative 1 to 1. We're increasing from 1 to infinity. So now, that 0.10 we know is a min. Let's go ahead and sort of bottom that out, right? We know we're increasing on the interval negative infinity to negative 3, so we have to cross through that point, negative 5, right? Let's go ahead, put something through that. From here, what else do we know? We have a max, and it looks like, right, at negative 3, which our derivative test confirms. So why don't we go ahead and calculate what our function is at negative 3. We find that our function is 32. So let's go up here and mark that. Now we know we're going to do something like that through here. We know we have an inflection point here, right, along negative 1 and infinity. I mean, along the line x equal to negative 1 is what I'm trying to say. We have an inflection point. So why don't we go ahead and calculate what our function is at negative 1? It's going to be 16. So since we have an inflection point, we know we go from being concave up to being concave down to being concave up. This tells us what our inflection is going to look like. It's going to be something like this, right? Agreed? From here, we just have to connect like that. We know we're increasing through there. So notice we only have to calculate 3 different values. Really, I guess 4 different values because of the negative 5. But using all of this information, we get something that looks like the graph of this function. Now jumping to what this graph looks like. Hey, check it out, lo and behold, does in fact look the same. Now points on all of this, because y'all are for sure asking yourselves this. When are we ever going to use it? I'm going to be honest with y'all, you're not. This, your computer will do for you. So what's the point of this? What do y'all think the point of learning all of this is? What do y'all at home think?
You'll understand the information your computer gives you?
Partially. What do y'all think in here? Yes, that's 110% it. It's just about learning how to think. That is all this is about. And I know that sounds condescending, but believe me, it's really not meant to be. What this is about is learning how to take very little information, right? Very little information, and making inferences from it to get the bigger picture. This is what's properly known as mathematical thinking. Mathematical thinking isn't just about math. It's logic. That's what it's really about. Mathematical thinking and logical thinking are the same thing. And this is just teaching you logical thinking, how to take very little information and pull out an infinity of information from it. Because think about it, that's what we've done here, right? Between any two of these points, there's an infinite number of other possible points. And you took very little and filled in the gaps. So to answer some questions that I'm sure y'all have, what is this for? When am I going to use it? You're not. Your computer will do this for you. What you're learning here is how to apply logical thinking, step-by-step orderly thought processes to a problem. So don't look at this and be like, oh, I've got to know this because I'm going to use it. No, don't try to find a use for it. What you're trying to learn is how to organize your thoughts and work from there. Having said that, let's look at another example. Let's not look at the, actually this is a good one. For those of y'all at home, we've got the function f of x is equal to x to the fourth minus 12 x to the third plus 48 x squared minus 64x. Going through everything, we find we have x-intercepts at x equal to 0 and x equal to 4. So that's going to be an x-intercept here, an x-intercept here. I don't need to write that one. Let's just write this one. Now, applying the first derivative, we find we have critical numbers at 1 and 4. So we have critical numbers x equal to 1. There. Now, applying the second derivative, we find we have inflection points at 2 and 4. Applying our first derivative test, we find we're decreasing on the interval negative infinity to 1. Increasing from 1 to 2. Let me expand that a little bit like that. Then we're increasing on 2 to 4. And we're increasing on 4 to infinity. Okay, So if we're decreasing on the interval negative infinity to 1, we automatically know our graph is going to have to go through that point in a decreasing fashion. We said that we had an intercept at 4, 0, which is the point of inflection, right? Moreover, it's just going to be a point of inflection. So we're increasing through here. So we know we're going to do something like this, right? Through there. What else do we know? We know we're concave up from negative infinity to 2. Concave down from 2 to 4, and concave up from 4 to infinity. So matches our picture so far, kind of, right? Makes sense what I'm saying? We also know we have a relative min at 1. So calculating our function, when x is equal to 1, we get negative 27. That's going to need to be somewhere way down here. At 2, we got an inflection point, so let's go ahead and calculate what our function is there. That's negative 16. It's going to be somewhere over here. So our function is going to look something weird like this. Now, let's compare this with our graph. Holy shit, it almost looks identical to that, right? Okay, so I could have drawn it better. This flattens out a little bit more. So it looks more like that, but otherwise, pretty on point. What do y'all think of this? How does this feel to y'all? Does it make sense? It's just about working with a little bit of information to get through these. It's a slow process, but if you have everything piece by piece put in front of you, it's straightforward. Having said that, we are past time, so I will let y'all go. If y'all have any questions, I'll stick around for a few minutes.